A metal ball rolls off a horizontal table 80 centimeters above the floor. If the metal ball had been rolling on the table with a speed of 35 centimeters per second, at what horizontal distance from the table does the ball land? And this sounds like a projectile motion kind of situation, similar to the last more sort of abstract formal question we had. So I've written down the results of that question. These are kind of the equations of motion for that situation where an object is rolling off of a table with a height h with an initial horizontal velocity v. But again, we have specific values here. I'm going to draw a picture again for this situation so we could talk a little bit about what's going on in this situation. So we have again this object here that is rolling. This is a metal ball, I guess, in this case. It's rolling at 35 centimeters per second. It rolls off the edge of the table, right? Maybe I should draw the rest of the table in here. Let's get kind of a table leg in here somewhere. I don't know how big 80 centimeters would be for scale, but it's going to roll off and kind of go through the air here and eventually land at some point over here. And we're neglecting air resistance, as we often do in this class. And I will say here in this space here, I'll put the label of the height of 80 centimeters that's given to us. But when it says, at what horizontal distance from the table does the ball land, let's recognize the question we're being asked about is basically this distance right here. So this is the thing we don't know that we're looking for. But with these two equations, I recognize that the horizontal velocity v is equal to 35 centimeters per second, and h is equal to 80 centimeters. And I like to look at these two formulas in these two equations as kind of functions, like x as a function of time t, y as a function of time t. So I wrote them with function notation, like you may have seen, kind of like f of x is a function of x, right? But here it makes more sense to have this notation, these variables, that is. And in that sense, I think it's okay. I give you permission in this class. If you want to just take these numbers and put them in as parameters, and when you do that, it's kind of convenient to sometimes leave the units out. So in other words, if I say, okay, I'm going to write what x of t really is, maybe put me in a comfortable math space by doing this and saying, here it is, 35 times t, right? And y of t, it turns out, what should that be, right? Well, we should say 80, and I said we had permission to leave out the units, and then it would be like minus 1/2 times 9.81. Wait a minute. Let's be careful there. It's okay to say minus 1/2, but if we're working in centimeters, g is equal to 9.81 meters per second squared, which can be converted into 981 centimeters per second squared. So it's okay to leave out units, but you have to be consistent. If you're saying I'm going to work in centimeters and seconds, you have to be consistent all the way through, which means the parameter g is going to be represented by the number 981 instead of 9.81. So make sure to have that correct there, and hopefully this notation is all understandable for everybody here, but then that's going to be multiplied by t squared. So those are my two functions. Okay, but now I might ask, how do I answer this question? Well, if I were to say, like, what do these two functions describe? If I were to just tick some random point here somewhere along this trajectory, I would say as an ordered pair in the coordinate system described by kind of an implied origin here, this ordered pair describes, as an ordered pair, the position here is being described by x of t as the first number and y of t in the kind of implied Cartesian coordinate system that I'm using, right? The question point that I'm looking at here, like, how would I describe that as an ordered pair? Well, I would say that is like x of t is equal to kind of the question I'm going after. Maybe I could call that the range, but I'm just going to put the question mark there. But what I know about y right there is that at that point, y has to be equal to 0. So its question mark is equal to 0. And if you like, you can, I'll just use question mark if everyone's cool with that. So if I make that, if I treat that ordered pair as kind of like representing the point that I'm looking at, and I therefore say, okay, so we've got, in terms of these two equations of motion, I've got question mark is equal to 35 times t, and then I've got 0, because I know the vertical position when it lands is equal to 0, is equal to 80 minus the 1/2 times 981 t squared. Now I've got a math problem that I think I might actually be able to solve. because one of the things I wasn't given here was at what time does it land? But if I look at this second equation right here, I think I can solve for that, right? Like this one, and I'm kind of running a little bit out of space here, but this one lets me say that, let's see, it would be like, what would it be? I think, I'm going to do a little algebra in my head if everyone's cool with that, but it says, I think if I isolated t squared, I'd have to like add this to both sides and then maybe multiply by 2 and divide by 981. So I'd get like 2 multiplied by 80, if you followed all of that, divided by 981. And that really means that t is equal to the square root of all of that, 2 times 80 over 981. So that's something that now I can go to my calculator, and my calculator will work all the magic of figuring out what that is, and I get a value of like 0.40. I always keep a few extra here. This is not a final result, so maybe 386 I'll round off to here, and that should actually be in seconds. I start bringing units back at some point, so I'll put a seconds there just to make sure. And then if I take that value for time and I say, hey, I still have this question mark, right? Now I can go and plug that in and say, okay, take 35 multiplied by, let me use parentheses for this multiplication, multiplied by 0.403, and maybe I have to be a little bit careful here because I've kind of like left out units at various places, but I'm just going to do that, and again, I'm running out of space, so I'm going to go down here, and my calculator says that that's about 14.1. This is actually my final result, so I'm ready to just round that off at 3 significant digits. But I left out some of the units here, so I have to be careful with that. All final answers must have units. This was 35, right, was really centimeters per second. I'm calculating a distance multiplied by 0.40, etc. in seconds. So this should be in centimeters if you track all those units through there. So I've got 14.1 centimeters. Let me see if I can squeeze a box around that. This corner of my pad is a little hard to draw on sometimes for me because I'm right on the edge of it. But we've got 14.1 centimeters. There it is.